Chapter 2: Data and Sampling Distributions. This chapter delves into the principles of data sampling and the behavior of sample statistics. In an era of big data, it may seem that sampling is obsolete, but in fact, it remains a vital tool for ensuring data quality, minimizing bias, and working efficiently. Key concepts: random sampling, the process of drawing a subset, a sample, from a larger data set, the population, where each member of the population has an equal chance of being chosen. This helps ensure the sample is representative and minimizes sample bias, where a sample misrepresents the population in a systematic way, e.g., the 1936 Literary Digest poll. Selection bias. This refers to the systematic error that arises from choosing data non-randomly, which can lead to misleading conclusions. A common form in data science is the vast search effect, where repeatedly searching through data is bound to turn up something interesting purely by chance. Sampling distribution. While a data distribution is the frequency distribution of individual data points, a sampling distribution is the frequency distribution of a sample statistic, like the mean, over many samples drawn from the same population. The central limit theorem. This fundamental theorem states that as the sample size increases, the sampling distribution of the mean will tend to follow a bell-shaped normal curve, even if the original data distribution is not normal. This allows the use of normal approximation formulas for statistical inference. Standard error. This is the standard deviation of a sample statistic's sampling distribution. It measures the variability of the statistic from sample to sample and decreases as the sample size increases. It should not be confused with the standard deviation of the data itself. The bootstrap. A powerful and flexible resampling method used to estimate the sampling distribution of a statistic. It involves repeatedly drawing samples with replacement from the original sample data and recalculating the statistic for each resample. This allows for the construction of confidence intervals, a range that likely contains the true population value, and the estimation of standard error without relying on theoretical formulas or assumptions about the data's distribution. Key probability distributions. Normal distribution, the iconic bell curve. While most raw data is not normally distributed, many statistics, like sample means, are. QQ plots are used to visually check if a sample conforms to a normal distribution. Long-tail distributions. Many real-world phenomena, e.g., stock returns, income, have distributions with long tails, meaning extreme events are more common than predicted by the normal distribution. Binomial distribution models the number of successes in a fixed number of binary trials, e.g., click, don't click. Poisson and exponential distributions. The Poisson distribution models the number of events occurring in a fixed interval of time or space, e.g., user arrivals at a website. The exponential distribution models the time between such events. Conclusion. Even with big data, understanding sampling principles is crucial for data quality and avoiding bias. The bootstrap method provides a powerful, computer-intensive tool to quantify the uncertainty in estimates without needing to make strong assumptions about the underlying data distribution. Familiarity with key probability distributions helps in modeling various data-generating processes. Chapter 3: Statistical Experiments and Significance Testing. This chapter explains the framework for designing and evaluating experiments, a cornerstone of statistics that is highly relevant to data science, particularly in areas like web testing. Key concepts. A/B testing. A randomized experiment with two groups, A and B, to determine which of two treatments, e.g., web page designs, prices, is superior. A control group, the standard or no treatment, is used as a benchmark, and subjects are randomly assigned to groups to ensure that any observed difference is due to either the treatment effect or random chance. Hypothesis testing. A procedure to assess whether an observed effect is real or simply due to random chance. Null hypothesis, HO. The baseline assumption that there is no real effect and that any observed difference is due to chance. Alternative hypothesis, HA, the counterpoint to the null, which is what the researcher hopes to prove. One-way versus two-way tests. A one-way test looks for an effect in only one direction, e.g., B is better than A, while a two-way test looks for any difference. A is different from B, either better or worse. Resampling, permutation test. An intuitive method for hypothesis testing. To test the difference between two groups, their data is combined and shuffled. Then, new random groups of the same size are repeatedly drawn from this combined data, and the difference in the statistic of interest, e.g., the mean, is calculated for each pair of new groups. This creates a distribution of differences that could occur by chance. The originally observed difference is then compared to this distribution. P-value. The probability of obtaining a result as extreme as or more extreme than the observed result, assuming the null hypothesis is true. It is not the probability that the null hypothesis is true. A low p-value, typically less than 0.05, suggests that the observed result is unlikely to be due to chance, leading to the rejection of the null hypothesis. The threshold for this decision is called alpha. ANOVA, analysis of variance. A statistical test used to compare the means of more than two groups simultaneously. It performs an omnibus test to see if there is a significant difference somewhere among the groups, which helps to avoid the increased risk of false positives that comes from running multiple A/B tests. Chi-square test. A test used for count data, typically in contingency tables, to assess whether the observed counts deviate significantly from expected counts under a null hypothesis. Multi-arm bandit algorithm. A modern alternative to traditional A/B testing, especially useful for web optimization. It allows for testing multiple treatments at once and dynamically allocates more traffic to the better performing treatments during the experiment, thus minimizing the cost of showing inferior options and reaching conclusions faster. Power and sample size. Power is the probability that a test will correctly detect a real effect of a specified size. Before running an experiment, data scientists often perform power calculations to determine the minimum sample size needed to have a good chance of detecting a meaningful effect, thereby avoiding wasted effort on underpowered studies. Conclusion. While data science often prioritizes predictive performance over formal statistical inference, understanding experimental design and hypothesis testing is crucial for any situation requiring a decision based on data, such as A/B testing. Intuitive resampling methods like permutation tests can effectively assess the role of random chance. While p-values should be interpreted with caution, they can still be a useful metric. For continuous optimization, modern methods like multi-arm bandits are often superior. Chapter 4. Regression and Prediction. This chapter focuses on regression, a core statistical method used to model the relationship between variables and to predict a numeric outcome. Key concepts. Simple linear regression models the relationship between a single predictor variable, x, and a response variable, y, using a straight line. The model is defined by an intercept, the predicted value of y when x is 0, and a slope, the change in y for a 1-unit change in x. Least squares, the most common method for fitting a regression model. It finds the line that minimizes the sum of the squared differences between the observed values and the values predicted by the model. 2. The residuals. Multiple linear regression extends simple regression to include multiple predictor variables. Each predictor has its own coefficient, representing its effect on the outcome while holding other predictors constant. Assessing the model. Root mean squared error, RMSE. The square root of the average squared residuals. It is the most important metric for evaluating the predictive accuracy of a regression model. R squared, R2, the proportion of the variance in the response variable that is explained by the model. It is more useful for explanatory power than predictive accuracy. T-statistic and p-value, used to assess the significance of each predictor's coefficient. A high t-statistic and low p-value suggests a variable is a meaningful predictor. Model selection. Stepwise regression, an automated method for selecting variables to include in a model. It iteratively adds forward selection or removes backward selection to find a model that optimizes a criterion like AIC, a Kaike's information criterion, which penalizes model complexity. Penalized regression. Methods like ridge and lasso regression prevent overfitting by adding a penalty to the model for having too many variables or overly large coefficients. Interpreting the model. Correlated predictors and multicollinearity. When predictors are highly correlated, it becomes difficult to interpret their individual coefficients as their effects are entangled. Perfect correlation, multicollinearity, can make the model unstable or impossible to compute. Confounding variables. The omission of an important predictor can lead to spurious relationships and incorrect interpretations of the coefficients of the included variables. Interactions. An interaction effect occurs when the effect of one predictor on the outcome depends on the level of another predictor. This is modeled by including an interaction term, x1 times x2, in the regression equation. Modeling nonlinear relationships. Polynomial regression adds polynomial terms x squared, x3 to the model to capture curved relationships. Spline regression fits a series of piecewise polynomials smoothly connected at points called knots. This is a highly flexible way to model nonlinear effects. Generalized additive models, GAMs, automatically fit spline regressions, freeing the user from having to specify the location of the knots. Regression diagnostics involve analyzing the residuals to assess the model's fit and check its assumptions. Partial residual plots are particularly useful for visualizing the relationship between the outcome and a single predictor, helping to identify nonlinearity. Conclusion. Regression is a versatile and fundamental tool for both prediction and explanation. While the basic form is linear, it can be extended with splines and polynomial terms to model complex, nonlinear relationships. In data science, the primary focus is on predictive accuracy, measured by metrics like RMSE on out-of-sample data, and care must be taken to avoid overfitting and correctly interpret the model in the presence of correlated or confounding variables. Chapter 5. Classification. Classification is a type of predictive modeling that aims to assign a record to one of a small set of predefined categories or classes. This chapter covers the most important techniques and evaluation methods for this task. Key concepts. Naive Bayes, a simple but effective classification algorithm based on Bayes' theorem. It calculates the probability of a record belonging to a class based on the probabilities of its predictor values occurring within that class. Its naive assumption is that all predictor variables are independent of each other, which is rarely true but often works well enough in practice. It is particularly effective for text classification, e.g., spam filtering. Discriminant analysis. A classic statistical method, particularly linear discriminant analysis, LDA, that finds a linear combination of predictors that best separates the classes. It works by maximizing the ratio of between-class variance to within-class variance. Logistic regression, one of the most widely used classifiers. It adapts linear regression to a binary 0-1 outcome problem. It models the log odds of the outcome as a linear combination of the predictors. The output is a probability propensity score between 0 and 1, which can then be converted into a class prediction by applying a cutoff, e.g., greater than 0.5. A key advantage is that its coefficients are interpretable as log odds ratios. Evaluating classification models. Simple accuracy, the percentage of correct predictions, is often insufficient, especially with imbalanced classes. Confusion matrix. A table that summarizes the performance of a classifier by showing the counts of true positives, true negatives, false positives, and false negatives. Precision and recall, sensitivity. Precision is the proportion of predicted positives that were actually positive. Recall is the proportion of actual positives that were correctly identified. There is often a trade-off between the two. Specificity is the proportion of actual negatives that were correctly identified. ROC curve and AUC. The Receiver Operating Characteristics curve plots recall sensitivity against the false positive rate 1 minus specificity at various cutoff levels. The area under the curve, AUC, provides a single number summary of the model's ability to distinguish between the classes. A perfect classifier has an AUC of 1, while random guessing has an AUC of 0.5. Lift charts. These measure how much more effective a model is at identifying the class of interest compared to random selection, often evaluated decile by decile. Strategies for imbalanced data. The rare class problem occurs when one class, e.g. fraud, is much less frequent than another. This can cause models to have high accuracy by simply predicting the majority class. Strategies to handle this include undersampling, training the model on a sample with fewer records from the majority class; oversampling and SMOT, training the model on a sample with more records from the minority class, often by creating synthetic data points, e.g. with the SMOT algorithm; weighting, assigning a higher weight to the rare class during model training to increase the penalty for misclassifying it. Conclusion: classification is a core task in predictive analytics. A variety of methods exist, from the simple naive Bayes to the workhorse logistic regression. The choice of model often depends on the data and the need for interpretability. Critically, evaluating a classifier requires moving beyond simple accuracy to metrics like precision, recall, and AUC, which provide a more nuanced understanding of performance, especially when dealing with the common challenge of imbalanced classes. Chapter 6: Statistical Machine Learning. This chapter explores powerful, flexible predictive modeling techniques that are data-driven and do not assume a predefined structure like linear regression. These methods are at the heart of modern machine learning. Key concepts: K-nearest neighbors, KNN. A simple and intuitive non-parametric method. To classify a new record, it finds the K most similar records, neighbors, in the training data and assigns the majority class of those neighbors to the new record. For prediction, it averages the outcomes of the neighbors. Its effectiveness depends heavily on the choice of K, the distance metric used to measure similarity, and proper standardization of the predictor variables to ensure they are on a comparable scale. Tree models, CART. Decision trees build a model by recursively splitting the data into more homogeneous subgroups based on the predictor variables. The result is a set of if-then rules that are easy to visualize and interpret. However, single trees are prone to overfitting, fitting the noise in the data, so their growth must be controlled, for example, by pruning or setting a complexity parameter. Ensemble learning. The principle that combining the predictions from multiple models, an ensemble, is often more accurate than using a single model. Two main approaches are applied to tree models. 1. Bagging and the random forest. Bagging, bootstrap aggregating, involves creating multiple models by training each on a different bootstrap sample of the data and then averaging their predictions. The random forest is a powerful enhancement of bagging for decision trees. In addition to sampling the data for each tree, it also samples a random subset of the predictors at each split. This decorrelates the trees and further improves accuracy. A key output is variable importance, which ranks predictors by their contribution to the model's performance. 2. Boosting. An alternative ensemble method where models are built sequentially. Each new model is trained to correct the errors of the previous models. It does this by giving more weight to the records that were previously misclassified. Stochastic gradient boosting is a highly effective variant that combines this sequential process with random sampling of data and predictors. XGBoost is a popular and computationally efficient implementation. Boosting can achieve extremely high accuracy, but is very prone to overfitting if its hyperparameters, e.g. learning rate, tree depth, are not carefully tuned using cross-validation. Regularization is a technique used in boosting to penalize model complexity and prevent overfitting. Conclusion: Statistical machine learning provides powerful, flexible tools for predictive modeling. While KNN offers a simple, instance-based approach, the state-of-the-art is dominated by ensemble methods built on decision trees. The random forest is a robust, easy-to-use, and highly effective algorithm. Boosting, especially XGBoost, can achieve even higher performance but requires careful tuning of its hyperparameters to avoid overfitting. These ensemble methods are often the winning choice for classification and regression tasks in data science. Chapter 7: Unsupervised Learning. Unsupervised learning refers to methods that analyze data without a predefined outcome or labeled response. The goal is to discover hidden structures, patterns, and relationships within the data itself. Key concepts: Principal Components Analysis, PCA, a technique for dimensionality reduction. It transforms a set of correlated numeric variables into a smaller set of uncorrelated variables called principal components. The first principal component is a weighted linear combination of the original variables that captures the maximum possible variance in the data. Subsequent components capture the remaining variance. By retaining only the first few components, we can reduce the number of variables while preserving most of the information. Scree plots and loadings, the weights, are used to interpret the components. Clustering, the process of partitioning data into distinct groups, clusters, such that records within a cluster are more similar to each other than to records in other clusters. Clustering, K-means clustering, a widely used algorithm that partitions data into a user-specified number, K, of clusters. It works by iteratively assigning each record to the nearest cluster center, mean, and then recalculating the cluster centers until the assignments no longer change. The elbow method can provide guidance on choosing an appropriate value for K by plotting the variance explained as K increases. Hierarchical clustering, an alternative approach that builds a hierarchy of clusters. The agglomerative method starts with each record as its own cluster and progressively merges the two most similar clusters until only one remains. The results are visualized in a dendrogram, which allows the user to see the cluster structure at different levels of similarity without pre-specifying the number of clusters. The way cluster similarity, dissimilarity is measured, e.g., complete linkage, average linkage, can significantly affect the results. Model-based clustering assumes that the data is a mixture of several probability distributions, typically multivariate normal. It fits different models to the data and uses a statistical criterion like BIC, Bayesian Information Criterion, to select the best model and the optimal number of clusters. Scaling and categorical variables. Scaling. Unsupervised methods that use distance metrics, like PCA and all forms of clustering, require variables to be on a comparable scale. Otherwise, variables with larger magnitudes will dominate the analysis. The most common method is standardization or normalization, which involves converting variables to their z-scores, subtracting the mean and dividing by the standard deviation. Categorical data. PCA and K-means are designed for numeric data. To use categorical variables, they must be converted to a numeric format, typically using one-hot encoding. For methods that can handle mixed data types, like hierarchical clustering, Gowers' distance is a useful metric that can calculate distances for both numeric and categorical variables by scaling them all to a 0-to-1 range. Conclusion. Unsupervised learning is a critical part of a data scientist's toolkit for exploring and understanding complex, high-dimensional data. PCA is the workhorse for dimensionality reduction of numeric data. For discovering groups, K-means is scalable and effective for large data sets, while hierarchical clustering offers more flexibility and an intuitive visual output for smaller data sets. Proper scaling of variables is essential for all these methods. The insights and features generated from unsupervised learning can then be used to build more powerful supervised predictive models.